Personal finance practice problem using OneNote. Rule of 72 and running balance calculation problem number 3. Prepare to get financially fit by using personal finance. Here we are in OneNote. If you have access to OneNote, would like to follow along, you're not required to, but if would like to, we're in the icon on the left-hand side in the Practice Problems tab down in the 1119 Rule of 72 and Running Balance Calculation Prob number 3 tab. Also note, when using OneNote, look at the Immersive Reader tool. Our presentations will also be in the text area with the same name, same number, but with transcripts. Transcripts that can be translated into multiple different languages and either listened to or read in them. Closing the icon, we got our information up top, calculation then on down below. We're looking at our present value, future value calculations. We'll be running this in multiple different ways. We have the information saying that the yearly earnings percent in a savings account is going to be the 18%. Now, generally, 18% is going to be high for a savings account, but we want to use the 18% given this is the third problem, and we want to use a higher rate than we had in the other two. Remember that any investment which we expect to be growing over time will have a similar scenario. So if we were to be investing in stocks or bonds, savings account, a CD account, or if we're investing in something like land or in our home, and we expect the value of it to be going up and an annual amount, this time we're going to be picking the 18%, we will have a similar scenario. We're going to then be asking the question of how long will it take for the account to double? So if we're looking at the 18%, then how long will it take for an investment to double in value? Using the rule of 72, we can approximate that answer without even having an investment amount. That's what we'll start off doing. And then we'll pick an investment amount, picking an investment amount, often allowing us to be more concrete as we think through this practice problem, meaning most people, if they use the rule of 72 and they just think about an abstract investment, it can be somewhat abstract thought in the mind. If you actually pick a concrete investment amount, it can be a little bit easier. Also note that if you're using a book problem then, and they ask you a question using something like the rule of 72 or asking you this idea of how long it will take for an investment to double, sometimes it's useful to pick an investment amount so that you can then calculate it basically different ways and mull it over in your mind as to what it actually means. Common investment amounts then would be something like 100, 1,000, 10,000 generally. We're going to then be picking an investment amount of 3,000 because we want to make it a little bit different than the problems we have looked at in the past, and note that we can then use different numbers as the investment amount for that kind of doubling concept. That means that our starting point for us is going to be 3,000. We're going to double it then. The doubling would be at 6,000. How long would it take for the 3,000 to get to 6,000? Let's first use the rule of 72. Straightforward rule. You basically simply take 72 divided by the rate. However, you don't take the percentage rate or the decimal rate. You got to convert it basically to a number. So we're going to put this into a table so that we can practice putting stuff into a table, and also make sure that we have a concrete understanding of what the percent means and what we need to do for the rule of 72 related to it. So we got the 72, that's what we're going to start off with because it's the rule of 72. It just happens to work with the rule of 72. And then we've got the rate, which is 18%, which we can put in the format of a percent, which would be 18%, or in the format of a decimal, 0.12. And then if we want to convert it to a number, then mathematically what you would do is multiply it by 100, which would in essence just simply get you 18. 18 not being a percent or a decimal in this case, just the number 18. Then you could take the 72 divided by the 18, and that would give you your approximate years for this to double, that being then the 4 years. So let's do that one more time. If you got the 0.18, that would be the 18%. If you multiply that times 100, that moves the decimal 2 places over, so you got the 18, flat 18. And then you can take the 72 divided by the 18, and that'll give you your 4, which will be the number of periods that you would expect to double. If you then use the amount of 3,000, you would expect it would take about 4 years for it to double, getting then to 6,000. That's one way that you can do this calculation. Let's do it another way down here, and that's going to be our running balance calculation. Also note that this rule of 72 is kind of an approximation, so it's not exact. And that's important to note because if you are working with a book problem, for example, it's a test question and they ask you to do the calculation for the rule of 72, they could force you to use the rule of 72, for example, by making it an approximation and making the answers be that approximation instead of the exact answer that you might get if you used some other method like a financial calculator or Excel or something like that. Or if you try to use the rule of 72 in a test question situation and they want an exact answer or an answer that uses something like tables, then again, they can kind of trick you or make it so that you get the wrong answer by making something more exact in that format. So just be aware that a test question can force you to use one or another method that they want you to use by taking into consideration rounding, which would be most likely irrelevant in most day-to-day normal real-life decision-making processes. Okay, we're going to do the same thing now, but now we're going to do a running balance calculation. This is very useful no matter what format that you do your present value calculations in, and I would highly recommend practice building these in something like Excel. These are difficult and time-consuming to do by hand, but easy to do in Excel, even if you have a long period, which we have only 5 years here, but even if you had a long time frame, they're really easy to build in Excel and quite useful of a tool to have. So what we're going to do then, we're going to say the starting investment amount is the $3,000, and we want to say how long is it going to take if I compound it yearly, year by year, to get to it to being doubled, which means that the investment amount has got to be clearing $6,000, twice the original amount of the $3,000. And we're just going to go year to year and watch it compound and take the 3,000 times 0.18, 3,000 times 0.18 is going to give us the 540. 540 plus the original 3,000 means that after 1 year, we'd have the 3,540. That's our new starting point, which we can then take and multiply times the 0.18 times 0.18. Before I do that, just note that if you have a problem, and this is similar to obviously like a tip or something like that you're giving to someone that you're tipping or something like that, then you could try to get to the end number directly without calculating the increase by saying 1 or 100% plus the 0.18, 18%. That would give us the 1.18 or 118% times the 3,000, and that will get you directly to the end result instead of having to calculate a two-step process. That could be useful when you're building tables or something like that with a complex table, and we'll see it in the future most likely. So we're going to say the 3,540 now and multiply that times the 0.18. That means interest for year 2 is going to be increased to $637.20 that we're going to have. If we take that and add it to the 3,540 we started with at the end of year 1, we're now at, after year 2, $4,177.2. If we take that as the starting point and multiply it times 0.18, we're then going to be getting the $751.90. And if we add that to our starting point of the 4,177.2, we're going to get now the ending point of the 4,929. Remember, we're trying to get this investment, see how long it'll take before this clears the 6,000, which will be our doubling point. So we've got that. Let's multiply that times the 0.18. That's going to give us about the 877.24. We're going to add that to our starting point. The end of year 3 is the 4,929.1. That's going to give us about the 5,816. So that's pretty close to the 6,000. I think we're going to clear it here. Then we're going to say times 0.18 for year 5. And that's going to bring us up to the interest of $1,046.94. Notice the interest going up sharply here because it's a fairly high interest rate at the 18%. And we're going to add that then to the 5,816.33. And that's going to give us our ending point, which does clear. And we are now over the top of that 6,000 at the 6,863. So you'll note when we calculated how long it would take with the rule of 72, we got exactly 4. It's not exactly 4. It's actually 4 something because we didn't quite get to the 6,000 after 4 years here. We got to the 5,816, cleared the 4 years, and then we're over the top of it in year 5. We could then use our table to estimate the fraction of a year, 4 point something, that we cleared the 6,000. But I won't do that now because, again, we just want to get an idea of the compounding of the interest with the use of the table. And we'll use more exact calculations when we get to Excel functions, calculating this, calculating using a mathematical formula, calculating it using tables.